All right, let's take a look at this example. We could break this up with partial fractions, possibly, and take a look at individual series. But I think I'm going to stay with the idea of the direct comparison test. Now notice I have an n times an n times an n. I have three linear functions here. So this is going to be n cubed in the denominator. N cubed plus I may or may not have a squared term and all that kind of stuff. So I want to compare this with 1 over n cubed, which I know 1 over n cubed converges. It's a p series of p equals 3. So what I need, because this converges, I need 1 over n times n plus 1 times n plus 4 to be less than or equal to 1 over n cubed. That implies that n cubed must be less than or equal to n times n plus 1 times n plus 4, which is clearly true, because if I multiply this out, I'm going to have an n cubed term plus a bunch of other terms adding to it. These are all positive terms, so this thing on the right has to be bigger than this thing on the left, which means this thing converges. Therefore, this infinite series is convergent by the direct comparison test with this series 1 over n cubed. Okay, here's another example. I need to figure out whether this is convergent or not, and I think I want to go ahead and stay with the direct comparison test. To me, this looks an awful lot like 1 over the square root of n, which is obviously 1 over n to the 1/2. Now this is a p series where p is less than 1, so I know that this is divergent. That is in fact divergent. So what I need to show then is that 1 over the square root of 3n minus 2 is greater than or equal to 1 over the square root of n. Because this is divergent, I need this guy to be bigger to show that that's also divergent. Otherwise, there's nothing I can do with it. So that implies that the square root of n must be greater than or equal to the square root of 3n minus 2. Square both sides, and I end up with n being greater than or equal to 3n minus 2, which is not true. For n equals 1, this is true, but for n equals 2, it's no longer true, because I get 2 on the left-hand side and 4 on the right. So this is actually a false statement. Therefore, what I just tried didn't work. So what if I modify this? Suppose I think about this and compare it to the sum 1 over the square root of 3n. Well, that's the same as the sum 1 over root 3 times 1 over n to the 1/2, which is just 1 over root 3 times the sum of 1 over n to the 1/2. This is still divergent. I know this is divergent because this is a p series, and I took a p series, so it's divergent, and multiply it by some real number. It's still divergent. So what I need to show now is the same thing. I need 1 over the square root of 3n minus 2. That needs to be greater than or equal to 1 over the square root of 3n. Well, that implies that the square root of 3n must be greater than or equal to the square root of 3n minus 2. Well, that implies that 3n must be greater than or equal to 3n minus 2, which it is. If I subtract 3n from both sides, I get 0 is greater than or equal to a negative 2, which is obviously true. Therefore, my original series is divergent by the direct comparison test, sorry we're not running out of room here, with the sum 1 over square root of 3n. Now notice when I did this, I justified up here, here it is, why that was divergent to begin with. If I couldn't have justified why that was divergent, then I shouldn't be doing this.